All right, so you're here because you really want to get what AGI is all about, right?
All right.
Not just the sci-fi stuff or like super technical jargon. You want the real deal.
Yeah, exactly. We're going deep on this one, taking a good look at
hmm
what the fuck is artificial general intelligence?
Catchy title.
It is, isn't it? By Michael Timothy Bennett. He's a researcher at the Australian National University. And it's a really interesting and provocative look at, all this hype and confusion around AGI.
Yeah, and we know you guys listening, you come from all sorts of backgrounds. Some of you are super techie, some of you, this is all new. So we're going to break it down, make it clear, and really focus on what matters.
Yeah, forget the Terminator stuff and even, the arguments about whether AGI even means anything anymore, like Melanie Mitchell talks about.
Right.
Bennett really gets to the core of this. He argues, and I tend to agree, that to really make progress on AGI, we need solid science, not just speculation.
Okay, so your mission, if you choose to accept it, and I think you have been tuning in, is to understand what AGI research is really about. We'll look at the tools they're using, the different ways researchers are thinking about building this general intelligence. So let's start at the beginning. What do we even mean when we say intelligence, and how does that apply to an artificial general intelligence?
Well, that's a surprisingly tricky question. Defining intelligence is hard. I mean, one way to think about it is like human-level performance on a ton of different tasks, right?
Right, like being good at everything a human can do.
Yeah, but that's kind of human-centric, isn't it?
Hmm.
And how do you even measure that across everything?
Yeah, it's a pretty high bar to set for anything.
It is. Now, Francois Chollet, he sees intelligence as this ability to adapt to new situations and learn new skills, at least as well as humans can. And he connects that to Occam's razor. The idea that the simplest explanation is usually the best, and this thing called Kolmogorov complexity. It's a bit technical, but basically think of it as the length of the shortest computer program that can produce a specific result. So a shorter program to do something could be seen as more intelligent.
So like being able to do more with less code.
Exactly. And Legge and Hutter, they have a similar view. They say intelligence is about achieving goals in a wide range of environments. And that also goes back to Kolmogorov complexity.
But Bennett has this interesting point about these definitions, that they might be, I don't know, a bit subjective.
Yeah, he argues that they often rely on an interpreter, something to make sense of the intelligence, like the hardware the AI runs on, or even us as observers. He makes this analogy. Imagine you have the AI, the software, right, and then the computer it runs on, and then the environment where it acts, which could even include us judging whether it did a good job. It's not just about the code itself.
So it's like you can't just look at the AI's code and say, oh, that's intelligent. You have to think about the whole system and the context.
Exactly. He calls this computational dualism, kind of like Descartes separating mind and body, where the pineal gland was the link. In AI, the theoretical Turing machine often plays that role, this like idealized computer.
So if those definitions have problems, is there a different way to think about intelligence?
Well, Bennett discusses this other definition by Pei Wang. He defines intelligence as adaptation with limited resources. It gets away from that software-hardware separation, but still captures the idea of being effective in different situations.
That makes sense.
And Bennett himself leans toward a definition focused on the ability to complete a wider range of tasks, adaptability, but also doing it efficiently. Like how quickly can it learn from data and how much energy does it use?
So it's not just about being able to do a lot of things, but doing them well and efficiently.
Right. And building on that, he says that AGI is a system that can adapt as broadly as a human scientist. Scientists have to identify problems, plan experiments, learn from the results.
Right.
That requires being autonomous, having its own goals, understanding cause and effect. And it also has to figure out when to explore new ideas versus sticking with what works.
So it needs to be both curious and strategic.
Exactly. And that's where typical AI techniques like supervised learning, where you learn from labeled data, or reinforcement learning, where you learn by trial and error, they fall short. And AGI, a true artificial scientist, needs to do all of that and more. So that brings us to the fundamental tools they're exploring to build this.
And Bennett says those tools come down to two key concepts, inspired by Sutton's bitter lesson: search and approximation. So let's start with search. What does that even mean?
So, put simply, search is about finding a solution within a set of possibilities.
Yeah.
Like when you're finding the best route on a map, you're searching through different paths until you find the one that gets you where you want to go. And in AI, it's more formal. We use algorithms like A. They use rules to try out different sequences of actions to achieve a goal. And we use heuristics to make the search faster. It's kind of like educated guesses, rules of thumb to guide the search.
So it's like a systematic way of trying things until you find what works.
Yeah, basically. And it's got some big advantages. The solutions you get from search are usually verifiable and interpretable. You can see why it arrived at a certain answer. It's great for planning, like in your GPS, proving mathematical theorems, and even learning by testing different hypotheses. Remember Deep Blue beating Kasparov in chess? That was largely about really powerful search algorithms.
Yeah, that was a big deal. But if search is so powerful, what are its downsides?
The main issue is when you have tons of possibilities, it gets really computationally expensive.
Makes sense.
And you can add constraints to narrow down the search, but that often takes a lot of manual work and doesn't scale well to open-ended problems. Plus, traditional search is kind of sequential. It doesn't fully use the parallel processing power we have now. The stuff originally built for graphics and games.
Right.
So search is best when you can clearly define the problem with a smaller set of abstract symbols or pieces.
Okay. And the other tool is approximation, which Sutton called learning, but Bennett says approximation is more accurate.
Yeah, approximation is what powers most of modern machine learning. You build a model that learns to map inputs to outputs by adjusting its parameters based on lots of training data. Think of neural networks learning to recognize images or large language models learning to write text.
Right.
They're finding patterns in data.
So they learn from examples.
Exactly. The good thing about approximation is it's great with noisy data and huge data sets. And it can use parallel processing really well, so it scales nicely on today's hardware. But because it learns patterns from data, it's always an approximation. It's not always perfect. And it can be hard to understand why it makes a certain decision. And importantly, these methods need a lot of data and energy. And they struggle when they encounter something very different from what they've seen before.
So they're good at recognizing familiar patterns, but not so great at dealing with completely new situations.
Exactly. And that's where the idea of combining search and approximation comes in. Bennett argues that systems that use both have the best chance of being more general and robust, more like real intelligence.
Interesting. So how do you combine search and approximation in a real system? What are some examples?
The big one is AlphaGo, the AI that beat the Go champion. It used search to explore the huge number of possible moves in Go, but it also used deep neural networks, which is an approximation technique, to evaluate how likely it was to win from any given board position.
So it's combining the ability to play the game with the knowledge of how to win.
Yeah, like that. Search provides the structure, approximation gives it the intuition.
That makes sense.
And Bennett talks about the simple grounding problem. It's how abstract symbols, like the word dog, get their meaning in the real world. Neurosymbolic hybrids try to solve this by using neural networks to process raw input, like pixels in an image, and translate it into symbols that search-based systems can then use for things like planning or logical reasoning. And the way you represent a problem symbolically can make a huge difference in how hard it is to solve.
Yeah, like choosing bad symbols could make even a simple task seem impossible.
Right. Then there's structured reinforcement learning. It uses approximation, things like convolutional autoencoders, to simplify complex sensory data into a symbolic form. This makes learning and adapting much easier. We're also seeing cool stuff with models like OpenAI's O3. It uses chain-of-thought reasoning, combining approximation with more structured steps. And DeepMind has alpha geometry, which uses neural networks and symbolic reasoning to tackle tough geometry problems.
Sounds like we're moving towards more sophisticated systems, instead of just throwing more data and computing power at the problem.
Yeah. Beyond these specific examples, there are these broader frameworks called cognitive architectures. They're like blueprints for intelligent systems, with different modules for perception, memory, reasoning, and decision-making. Some are even inspired by how human cognition works, like the difference between fast, intuitive thinking and slow, deliberate thinking. Bennett talks about older architectures like SOAR and ACTR and some really ambitious projects like Hyperon, ARAI, and NARS.
Those sound pretty comprehensive. What makes them different?
Well, take Hyperon. It's designed to be modular and distributed, using probabilistic logic, neural networks, and this thing called a knowledge metagraph to create a more complete understanding. It's built to be scalable and easily integrate new technologies. AIR is focused on self-programming and reflection, like the system thinking about its own knowledge. It puts a lot of emphasis on analogy, causality, and adapting to new situations by predicting what will happen. NARS is different. It uses a non-axiomatic logic, which is kind of a different way of thinking about logic, to deal with incomplete and uncertain information. It's all about learning and adapting in real time when you don't have all the information or resources you need.
So they each have their own philosophy on how to combine these different methods to create general intelligence.
Right. Hybrid systems have some advantages, like being more efficient, easier to understand, and being able to use human knowledge directly. And they can be more autonomous. But Bennett also mentions some challenges like how to really integrate these different methods effectively and making sure they're not just ad hoc solutions. And that brings us to meta approaches.
Okay, meta approaches. That sounds like it's about the big picture thinking behind building AGI.
Exactly. They're like the guiding principles, the philosophies behind how we should approach building intelligent systems. It's not about specific algorithms or architectures. It's about the overall strategy. Bennett divides them into three categories: scale maxing, simp maxing, and totally maxing. He links them to Sutton's bitter lesson, Occam's razor, and his own idea called Bennett's razor.
Okay, so let's break those down. First, scale maxing. What's the idea there?
Scale maxing basically says that the way to intelligence is to just keep making things bigger, more data, more computing power, bigger models. Bennett even jokes about it, calling the recent progress with huge language and vision models the embiggening. And a lot of this is thanks to the advancements in hardware that were originally driven by the gaming industry. We've seen some amazing stuff come out of this, like GPT-3 writing coherent text, and AlphaFold 2 predicting how proteins fold.
So the thinking is just keep scaling things up and eventually we'll hit AGO.
Pretty much. Yeah. But Bennett points out that we're probably reaching a point of diminishing returns with scaling. Those massive models use a ton of energy, and they still struggle with tasks where there's not much data to learn from, or situations that are very different from what they were trained on. The bitter lesson suggests that scale will eventually work, but eventually is doing a lot of work there.
Right, it might get us there, but it could be a long and expensive road. What about simp maxing? That sounds like it's about keeping things simple.
Exactly. Simp maxing is all about maximizing simplicity. The idea is that simpler models are often more generalizable, they work better in more situations, and they're more robust, they don't break as easily. In AI, simpler models can often be represented with shorter computer programs. This leads to the idea that intelligence is connected to being able to compress information efficiently. This is behind techniques like regularization, which prevents models from getting too complex and overfitting the data. And there's the minimum description length principle, which says that the best explanation is the one that describes the data in the shortest way possible.
And that ties back to Kolmogorov complexity, the shortest program thing, right?
Exactly. And there are these ideas like universal artificial intelligence, UAI, and theoretical frameworks like AIXI. They formalize this idea that the most intelligent system is the one that operates using the most compressed representation of its experiences. Ley-Hutter intelligence and Schulitz's measure of intelligence are also based on Kolmogorov complexity.
So the smartest system is the one that can learn the most from the least amount of information.
Yeah. But Bennett has some criticism of this view, too. He says it might be another form of computational dualism, focusing too much on the form of the program instead of how well it actually works in the real world.
Okay.
And calculating Kolmogorov complexity perfectly is impossible in theory. And it depends on the specific computer you're using. But he does admit that simpler forms often do generalize better in practice, probably because any finite system has limitations, and simpler forms tend to capture more general rules.
So simplicity is good, but it's not the whole story. And that brings us to W maxing. What's that all about?
So W maxing, or maximizing the weakness of constraints, takes a different approach. It focuses on how the intelligence system interacts with its environment. It's not just about the mind or the algorithm, it's about how it works in the world. This is similar to ideas like enactive cognition, which says that cognition is shaped by the interactions an agent has with its environment. And Bennett brings up pan-computational enactivism, which basically shifts the focus from internal computations to the relationship between a system's form and its function in a specific environment.
So it's not just what's going on inside the AI, but how it interacts with the world and learns from it.
Right. The key idea is that the ability to generalize, to handle new situations, comes from having fewer strict rules about how the system operates. This makes it more flexible. And Bennett argues that dunaxing isn't opposed to simp-maxing. In fact, optimizing for weak constraints can actually lead to simpler overall forms that embody those constraints.
That's interesting. Can you give an example?
Well, in some experiments with learning binary arithmetic, just using dunaxing actually led to better generalization than just using simp-maxing. W-maxing also means giving more control to lower levels of abstraction, which is similar to how biological systems self-organize. Like, think about the flexibility you get when you program in a language like C. where you have more control over the hardware compared to a higher level language like Python,
Yeah.
or compare a field programmable gate array, FPGA, which is very flexible, to a fixed architecture processor.
Okay.
And Bennett talks about examples like soft robotics, where you get complex behaviors from simple, flexible components and self-organizing nanoparticles.
So it's letting intelligence emerge from a more basic level instead of trying to program it in with strict rules.
Yeah. And because WMaxing doesn't separate software and hardware so strictly, it might lead to systems that are more efficient with data and energy. He even connects it to how biological systems explore the space of possible forms during development and regeneration.
That's fascinating.
And he points out that this inactive view, looking at how systems interact with their environment, has been used to explain things like causal reasoning, language, and even consciousness.
So wrapping up, what's the main takeaway from Bennett's analysis of all this?
He concludes that while scale maxing has been the dominant approach in AGI recently, all this embiggening, we're probably hitting a wall. These huge models are really expensive to run, and there are a lot of real-world problems where we just don't have enough data to train them effectively. So being efficient with data and energy is becoming more and more important.
So maybe just making things bigger isn't the ultimate answer.
Maybe not. He thinks WMaxing and SIMP-maxing are promising alternatives. And we're already seeing hybrid models that move beyond just data-driven approximation, like the O3 model. And with all the interest in developing autonomous agents for different applications, the ideas behind architectures like Era, NARS, and Hyperon, which focus on more integrated and adaptive intelligence, could become even more important.
So it's probably not going to be one single breakthrough, but a combination of different tools and approaches that will eventually lead to a true artificial scientist.
Yeah, most likely. While scale maxing has gotten us pretty far, the future of AGI probably depends on a combination of different strategies, using the strengths of search, approximation, and these different meta approaches.
This has been a really insightful look at some of the core ideas in AGI research. You definitely get a lot more out of it than just reading the headlines.
Absolutely.
And for you listeners, here's something to think about. We've talked about scale maxing, SIMP maxing, and W maxing, and these hybrid systems that combine search and approximation. Which approach do you think is the most promising for AGI? And why? Something to consider long after our deep dive ends.